Okay, starting from this lecture, we're going to talk about binary distillation. Okay. So, in binary distillation, in distillation in general, we have a feed mixture that is separated into at least two products by thermal means, right? So this figure here give you a schematic of a how a batch distillation is done. We have a vessel here that contains a mixture of many different components. Then you are heating this vessel with a heat source, right? Here, this is like a flame. Then you're going to produce a vapor. This vapor phase will enriched with the more volatile component, okay? And this vapor will leave this vessel, and we call this vapor as the overhead distillate, okay? This overhead distillate, in this case, will be condensed back into a liquid in this vessel, okay? Then what is left over is a bottom product that is enriched with the less volatile component, okay? So, excuse me. So in this particular case, the feed is a liquid, but in actual operation, the feed could be a liquid, a vapor, or a vapor-liquid mixture, okay? And the distillation can be done by a batch process as shown here, or it can be done by continuous process, okay? So distillation has very long history. By the 11th century, distillation was used in Italy to produce alcoholic beverages, right? So in fact, today, if you wanted to, you can brew a beer at home by fermenting barley, right? But if you were to produce alcohol, right, liquor with high content of alcohol, then you need to do a distillation process. Okay. So distillation has very low thermodynamic efficiency. The reason being that in this case, when you separate these two or more components, you basically produce a new phase, right? You either vaporize part of it and then you condense it, right? So this phase creation are very energy consuming, so it has a very low thermodynamic efficiency. So in a lab, distillation can be done by a device apparatus that looks like this, where you have this vessel, heat it up, produce a vapor, and this vapor can be condensed and become a liquid. Then this liquid will be enriched with the more volatile component, and what is left behind will be composed of the less volatile component, right? So this is what it looked like in real life. So in industry, multi-stage distillation is the most widely used industrial method for separating chemical mixtures, right? For example, petroleum refineries or your biochemical industry to separate small molecules, right? For example, this picture shows a schematic of the distillation column used in the petroleum industry, basically to refine crude oil, right? So crude oil is fed into this tower, okay, which is, in this case, it's a tree tower made with many different trees. And it will be heated up. So the more volatile component will goes up as a vapor, okay? Then the less volatile component will stay and leave the tower as a liquid. So in this case, this is a multi-stage distillation, okay? So we have many different stages that operate at different temperatures, okay? So basically then, as it goes up, temperature decreases, then you will have your exiting component with lower boiling point, That's how we can produce fuel oil, diesel, and or even less small hydrocarbons like butane and protein from petroleum, right? And this is what a real distillation column or tower look like in industry, right? So it's kind of they are very, very tall. And distillation is very energy intensive, especially when the mixture contains components with a relative volatility that's quite low. Okay, and the column can be treated, right, in this case, or it can be packed just like the absorption tower, the absorption and stripping tower. So by doing this multi-stage distillation, we can produce very pure products, right? Because in this case, each stage functions like as we discussed previously in the single stage equilibrium process, right? In single stage equilibrium process, and we talk about single stage flash that can separate a mixture, a binary mixture with very large or very small relative volatility quite well, right? But when the relative volatility is kind of close to one, then you have to do it in multi stages to achieve the desired separation outcome. Okay, so in our class, we're going to analyze a binary distillation using graphical methods with some assumptions, right? Because binary distillation is the simplest case and it's most well understood, right? And we will use binary distillation as an example system to introduce many of the important concepts to analyze distillation column, right? And if you work for industry, you will be using a process simulator to do the actual design of a distillation column. But many of the concepts we've learned in our class can be applied to doing those simulations. Okay, so let's look at the structure of a distillation tower. So here we have a distillation tower. In this case, it's a trade tower. And we have a feed that can be vapor, liquid, or mixture of vapor and liquid that's feeding to this tower by mechanical work. Okay, so then the liquid phase, right? That's typically the heavier, the phase with higher density, well, basically flows down, whereas the vapor phase, will go up, okay? Then the vapor will leave the column and entering a condenser, right? In this condenser, the vapor will be partially or fully condensed back into a liquid. Then it's gonna go into a reflux drum. This reflux drum will basically split this stream into two streams. One goes back to the column or tower. The other leaves the process and as a overhead product, right? It's also called tops or lights or distillate, okay? And then at the bottom, so the liquid comes down and it's gonna enter a reboiler, okay? And in which we're gonna feed some energy and to heat it up and produce vapor, right? And the vapor will go back. Meanwhile, we will also split the produced stream, partially and return it back to the tower and partially discharge it as a bottom product, which contains components with less volatility, okay? So here we input some energy to reboil to boil the liquid. And here, when we condense the vapor, we take some energy out, okay? So in the distillation column, the separation requires several conditions. First of all, we need to have a second phase, right? If you have a mixture, then you already have two phases. But if you have a single phase, for example, if you have a vapor, then you need to produce a liquid. If you have a liquid, then you need to produce a vapor, okay? So in the distillation column, liquid and vapor, they make contact while flowing countercurrently, right? That means when we return this liquid stream back to the tower, right, they are coming down and pass through every stage. During that process, they are making contact with the upcoming vapors, right? Then mass transfer will happen between them. Okay. Then at the bottom, similarly, when the rebroiler produces vapor and vapor goes up, and it's gonna make contact with the downcoming liquids in every stage, the mass transfer will happen between these two phases, right? And here, the components need to have different volatilities. So the more volatile component will prefer to stay in the vapor phase. So it will leave liquid phase, enter the vapor phase, then goes up until it gets condensed and leaves the process. And less volatile component will prefer to stay in the liquid phase, right? And flows all the way to the bottom and then leaves the process as a bottom product. Okay. So as you can see here, this operations is similar to in absorption and stripping tower. Here the difference is in absorption and stripping tower, right? For example, in the absorption tower, we feed a gas stream, right, from the bottom of the tower. Then we feed a liquid absorbance. That's the second phase from the top of the tower, right? So when the liquid absorbance coming down, it makes contacts. It makes contact with the upcoming gas phase, okay, at every stage in the tower, and the solute is transferred from the gas phase into the liquid phase, right? Whereas in this case, if we have a single phase, right? For example, if we have only a liquid phase, then we need to vaporize partially that liquid phase to produce as a vapor, so that vapor can goes up, and then the rest liquid can come down, right? If you have a vapor phase, then similarly, you need to condense that vapor. If you have a vapor phase, you need to condense that vapor, and you produce a liquid that can come down, right? So this liquid, when it comes down, it makes contacts with the upcoming vapor. So the mass transfer happens between them. Okay. Now let's look at one example from your textbook. Okay. So here we have a trade tower for distillation, and we have a feed that contains 46% more of benzene and 55% of toluene. Okay, and so they enter this column. Now, one question is, which is more volatile, right? Benzene and toluene, which is more volatile? Okay, so answer is benzene, because benzene basically ends up in the distillate. Okay, so when the vapor goes up, it enter a total condenser. So and it's being so the vapor will be condensed into a saturated liquid, which is partially returned back to the tower. That's called reflux, right? And partially discharged as a distillate, right? In this case, it contains 99% more of benzene. So benzene is the more volatile component. So it's reached in the upcoming vapor. Okay. And we have two products. So we have a liquid distillate of reached in benzene, and we have a liquid bottom that's enriched with toluene. Okay. So this tower has a total of 25 trees. It has a total condenser and a partial reboiler. Okay. So, and we can read the operation parameters, including the flow rate and the reflux ratio here. That's basically when the reflux drum split the stream here into two streams, and the reflux ratio is the ratio of the reflux versus the ratio of the ratio of the reflux flow rate versus the distillate flow rate. Okay. And then the operating pressure of this column is slightly higher than 1 atmosphere pressure. And it has a range, right, from 124 to 141 kilopascal, right? There's a pressure gradient, from bottom. So basically, brush pressure decreases from bottom to top, and there's a pressure gradient across every tree. Why is that? The reason being that in each tree, the vapor go through the tree, and the tree is loaded with a liquid. So the vapor will go through the tree, but the tree is loaded with a liquid. So the vapor needs to overcome the basically the resistance to flow through the liquid, right? So you need to have a pressure drop across each tree to provide that driving force. Okay. So here we have a feed that's at a bubble point liquid. So it's a pure liquid. So this bubble point liquid, when it enters the column, when it enters the tower, it will undergo a adiabatic flash process and produce vapor. Okay. So during that process, pressure drops, right? And because the feed has a higher pressure than the tower, temperature also drop. Why is that? Right? Remember when we talk about when in the single stage equilibrium process, we talk about adiabatic flash and isothermal flash, right? For adiabatic flash, there's no energy input or output during the flash process, okay? Since we have a pure liquid, as it vaporizes, right, the energy for the vaporization comes from the liquid itself. So the temperature of the liquid needs to drop to supply that energy, right? And we can actually compute the vaporization ratio, right? Remember that this is something we've talked about in the adiabatic flash process. Okay, we have a total condenser, right? That condenses basically all the vapor entering this condenser into liquid. We have a partial reboiler, right? That means basically when the liquid gets out from the column and enter the reboiler, we're gonna produce we're gonna partially vaporize that liquid, right? So we're gonna produce basically a vapor phase that's in equilibrium with the liquid phase, and the vapor will be feedback recycled back to the tower, whereas the liquid will be discharged as a bottom. But partial reboiler, it functions as an additional stage, just like every tree here. Why is that? So the reason being that when you have a pure liquid stream comes out, right, and you partially vaporize it, that's like a single stage flash process, remember? So we will produce a vapor that is rich with a more volatile component compared to the liquid stream, right? So you will do some additional separation between the two components you feed into this tower. So in this particular case, the feed happens, we feed this saturated bubble point liquid at between tree 12 and 13. Why is that? So this is basically something we're going to talk about later. So the feed location is actually a very important design consideration we need to consider when we design a distillation column, right? So for this particular case, we have 25 number of trees, right? We have a relatively volatility that's range from 2.26 to 2.52. So why we have a different volatility? Why we have the range? There are two reasons. One of them is that basically temperature at each stage is different, right? So the higher we are in this column, the lower the temperature is. Secondly, the the composition will be different, right? So we know the P value for a real system is a function of pressure, temperature, as well as composition. So that's why you have different P values, therefore different relative volatilities, right? But for the case where pressure change is small, temperature change is small, and a system that's close to ideal system, you will have a small change in K value, therefore you have a small change in relative volatility. Okay, so in this case, for this relative volatility, we need 25 trees. However, if you have a binary mixture with relative volatility that's close to 1, for example, smaller than 1.05, you need to have hundreds of trees to achieve a desired separation outcome. Okay, so this table shows many like different binary mixtures that can be separated by binary distillation operation in the industry, right? And it's listed in the order of an increasing relative volatility. Okay. So one takeaway from this table is that, as you can see here, as you increase the relative volatility, you tend to require less number of trees, right? Whereas with low relative volatility, you tend to have more number of trees, right? This is like close or more than 100 trees, whereas on this end, it's only, tens of trees. So let's look at another example, right? So here, we're trying to separating a feed, hydrocarbon feed with different hydrocarbons with different chain lengths from C2 to C6, right? So they are going to have different volatility because they have different molecular weight and length. So we use a 3-stage process to separate them. So the feed 1 is a mixture of C2 to C6. After the enter column 1, the feed is split into 2 streams. We have this product stream 2 that is rich in C5 and plus, right? So as you can see here. So we have another stream 3, that is rich with more volatile components, right? That's from C2 to basically C4. Okay, so we feed stream 3 into column 2. Again, the more volatile component will leave the tower from the top. In this case, it's C3, right? So we have mostly C3 in the stream 4. So we have the less volatile component goes to the bottom in the stream 5. And it's made of mixture of mostly butyl. This is butane. Okay. Then we enter the last column, the distillation column, that will separate normal butane from isobutane, right? Because normal butane is less volatile than the isobutane. Okay. So when we design a distillation column, there are a number of factors we need to consider. First, we need to know the feed composition. That includes feed flow rate. First, we need to know the feed condition, right? That includes feed flow rate, its composition, what temperature and pressure it's at, and what is the phase condition. Is it a pure phase, right? Pure liquid or a vapor, or it's a 2-phase mixture, right? If it's a pure phase, right? For example, if it's a pure liquid, is it a subcooled liquid or it's a saturated liquid? If it's a vapor, then if it's a vapor, is it a saturated vapor or it's a superheated vapor, right? That's a phase condition. We'll talk about the difference here later. Now, we also need to know the desired separation, right? You need to know for your distillate and for your bottom, what is the desired mole fraction of your product. Okay. And tower type, is it treat or packed? What is the operating pressure? What type of condenser and reboiler you're going to use? If it's partial or total, right? Partial means for the condenser, you only condense part of the vapor, and total means you condense all of the vapor into liquid. Right? Similarly for reboiler. Number of stages, right? For a tree tower, how many stages do you need? What's the minimum stages? Minimum number of stages. What are the actual number of stages to achieve the desired separation outcome? What is the reflux ratio, right? What is the minimum reflux ratio and what's the actual reflux ratio, right? Again, reflux ratio is basically the ratio of L over D, right? And when the vapor leaves the column and it enters condenser, then it enters a reflux drum, which is not drawn here. This reflux drum will split the stream into a distillate. That's our end product, and a liquid that goes back to the tower. Okay. So next, we're going to talk about the McCabe telegraphical method to analyze treat tower.